All right, everybody. I wanted to talk a little bit about this is going to be lecture B for chapter 9. And I just want to talk about a couple of things. We'll do at least a worksheet. There's going to be more lectures posted. Depending on how quickly I post these lectures, I might grant a couple-day extension for you guys. I'm not sure yet, but I'll definitely get back to you on that. So let's start with this worksheet, which is over here. If I'm looking away, it's because I'm on two screens, as I've mentioned before. So let's make this big so you guys can see that. I think my mic is working. Let me double check. Yeah, mic is working. So this should be recording. So we're going to talk about some sample t-tests. So what you want to do is you want to work through the t-test here. And so the t-table, the degrees of freedom are listed in the far left column, which is right here. The level of significance for a one-tailed test top and two-tailed test bottom is listed for each column to the right to the right of the degrees of freedom. So to read the table, you simply need to know the level of significance and degrees of freedom and the test. Now, if you're stuck here, you might be looking at, you probably want to look at our unit normal table, but I'm going to walk you through how to go through this worksheet. So give me just a second, because apparently this is not working the way I was expecting. All right, so let's go back to our screen share, everybody. So here we go. All right, so you should be able to see that now, I hope. I think you guys can all see that. Okay, so here we go. So for number one, if our degrees of freedom is 8, and this is based on our unit normal table, so you can check your answers based on what I'm putting in here. The 0.01 would be 3.355, okay? This is more for you to, this is just literally looking at the unit normal table. So we're listening to critical values for a two-tailed test at a 0.01, 0.05, and 0.10 level of significance. Again, the unit normal table will tell you the answers, but you can check it against this recording. 2.306 is going to be our 0.05 level of significance, and for degrees of freedom 8, it'll be 1.860. Now, again, referring to our unit normal table, we're literally going to do the same thing here. We're going to say degrees of freedom is 20, so it's 2.845. And then over here, we're going to have 2.086. So if this doesn't make sense, pause me. You want to look at your unit normal table, okay? Like I said, a lot of times I go over the answers on the homework, but ultimately when you get to the test, you have to know how we got there. So, so the first one, degrees of freedom, that for 40 is going to be 2.704. 2.704. And is that sharing right? I think that's sharing right. Let me double check. Yeah, that is absolutely sharing right. Okay, perfect. All right, so then that's 2.704. And then this one is going to be 2.021. And then this one is going to be 1.684. Again, unit normal table, totally posted. In case you have any problem locating it in your textbook. Degrees of freedom 120, 2.617. For 0.01 level of significance, this is 1.980 level of significance, and this, of course, is 1.658. So as the level of significance increases from 0.01 to 0.10, does the critical value increase or decrease? So take a moment, pause me if needed here. But your answer is going to be that the critical value in this scenario decreases. Our next question is, as the critical degrees of freedom increase from 8 to 120, does the critical value increase or decrease? And we're going to say the critical value decreases. Now you can see that if you look at the chart above. So the next thing we're asking is, how is this related to power? Now, if you're trying to figure this out before I walk you through the answers here, look at the sections, let's say these sections, refer to the sections that in chapter 9 for a review of factors that influence power. So if we're not sure, what you want to think about is really as the sample, I would say as the sample size increases, the degrees of freedom increase, thereby increasing the power to detect and effect. This increases power by reducing the cutoff for the rejection region. The rejection region is larger. And then you also want to think about similarly, if I can spell today, similarly, as the level of significance increases from 0.01 to 0.10, the cutoff for the rejection region is reduced, making the rejection region larger, thereby increasing power. So the next thing we want to talk about is comparing the Z and the T. So for the following degrees of freedom, list critical values for a one-tailed and two-tailed test at a 0.05 and 0.05 low significance. So a one-tailed test would be 2.326. Again, check this against the unit normal table. A 0.05 would be 1.645 one-tailed test. And for this one, this would be 2.576, and this would be 1.960. Again, you're just looking at that. Now, what we want to ask is, how do the critical values you listed in the previous question compare to those listed for the Z distribution, and explain that? Well, the way you can think about that is the critical values are identical, give or take rounding, and the reason for that is this is because a T, you should probably italicize, a T distribution with degrees of freedom equal to infinity is a standard normal Z distribution. Okay. So the next thing that we want to look at is, this is a little bit more conceptual. Okay. So the next thing that we're going to talk about is for this chapter, and this is still 9. Let's just say this is still chapter 9. So independent or dependent samples exercise. So for each of the following research questions, you will read an independent and dependent sample study to test that researcher question. You want to identify which study used independent and which used dependent samples. So let's walk through that. All right, so let's go back to sharing here on our desktop. All right, so the next thing we want to talk about is, how does winning influence self-efficacy or belief in one's ability among high school students? So, study 1, researchers hypothesized that the more wins a team has, the more teammates will believe in their own abilities or self-efficacy. To test this, they selected a group of sports athletes with few wins during the previous season, and a second group of sports athletes from teams with many wins during the previous season. They tested whether self-efficacy significantly differed between the groups. So let's walk through this one. So our study 1 would be independent samples, and study 2 would be dependent or related samples. So again, this is just more conceptual. So thinking about that, it's like that. Study 1 and study 2. Study 2, researchers hypothesized that the more wins a team has, the more teammates will believe in their own abilities or self-efficacy. To test this, they measured self-efficacy among athletes during a winning season and again during a losing season the following year. They tested whether the difference in self-efficacy between winning and losing seasons was significantly different. Well, for this one, study 1 would be a dependent related sample study, and study 2 would be an independent sample study. Like that. The next thing we talk about is, will levels of the brain chemical dopamine increase in response to food rewards? Well, study 1, researchers hypothesized that dopamine would increase to a high-fat food reward versus a similar low-fat food. To test this, they presented 4 adult female Mack fascicularis monkeys with a high and low-fat raisin and measured the level of dopamine in the brain in response to each reward. They tested whether the difference in dopamine levels was significantly different. Well, for this one, study 1 would have been independent samples, and study 2 would have been dependent or related samples. So what you want to be thinking about is how these are set up, and that's what makes them different. And actually, this is down here. You have to read this. So study 2, researchers hypothesized that levels of dopamine would increase in response to larger food reward. The tested state animals such as press a lever to receive a food reward and measure levels of dopamine in the brain in response to this reward. One group received a small food reward, and a second group received a large food reward, and they tested whether dopamine levels differ significantly between groups. So because we're comparing groups, these were those related samples, and then this one up here, because there was more of a control and a treatment, that's your independent sample study. So our next one is, do English as a second language children have the same knowledge of word meanings as English as a first language ELI children? So researchers hypothesized that ESL children would have greater difficulty in phonological awareness and the ability to notice, think about, manipulate the individual sounds and words. To test this, they had one group of ESL children and a second group of ELI children complete a phonological awareness assessment and recorded the scores. They tested whether phonological awareness assessment scores significantly differ between groups. Study 2, researchers hypothesized that ESL children would have the same knowledge of word meanings as do their ELI relatives. To test this, they recorded scores on a vocabulary knowledge assessment for ESL children and comparison ELI relatives of similar ages. They tested whether the difference in vocabulary knowledge assessment scores between these related children was significantly different. And for study 1 and study 2, the first one is going to be your independent sample study, and the second one is going to be your dependent or related samples. So this should be like this. And let's double check this one. No, this is actually, study 2 is more like that. The second one is like that. I got carried away, but here we go. Yeah, this should be like that. Okay. There we go. All right, so number 4. Got 5 of these, and that'll probably conclude our lecture. So how do psychosocial attitudes, those based on the interaction between the individual and the social environment towards romantic love, vary by race and culture? Study 1, researchers hypothesized that cultures focused on group identity, collectivists would place less emphasis on romantic love compared with cultures focused on individual identity, individualistic. To test this, they collected a sample of Chinese collectivists and American individualistic adolescents and had them complete a romantic love assessment survey. They tested whether scores on the survey significantly differ between groups. Study 2, researchers hypothesized that psychosocial attitudes towards love and individualistic cultures would be more negative following the loss of a romantic relationship. To test this, they recorded perceptions of love among a group of American college students during and following a romantic relationship. They tested whether the difference in perceptions of love during and after a romantic relationship was significantly different. Well, study 1 is independent samples. Study 2 is dependent or related samples. Kind of like that. And then our last one here is, does snacking between meals reduce the number of calories consumed in a meal? Study 1, researchers hypothesized that snacking between meals would only reduce calories consumed in the meal if participants thought of the foods as snack foods, referred to as cognitive satiety, like satisfaction. Clearly, I don't say that word real great. To test this, on day 1, they gave a group of participants 100 kcals of food they thought of as a snack food and recorded the number of calories consumed in the subsequent meal. On the second day, they gave the same group of participants 100 kcals of food they thought as a meal food and recorded the number of calories consumed in the subsequent meal. They tested whether the difference in calories consumed in the meal from day 1 to day 2 significantly differed. Study number 2, researchers hypothesized that snacking between meals would reduce the number of calories consumed in a meal. To test this, they recorded the number of calories consumed in a meal following one snack, group 1S, and the following 3 snacks, group 3S. The meal was buffet style, meaning that all participants would consume as much as they wanted in the meal. The researchers tested whether calories consumed in the meal significantly differ between groups. Well, study 1 is dependent or related samples, and study 2 in this case would be independent samples. So hopefully that is helpful. And just to make things really easy for you all, since we're not doing really a live class, this is what your answer should look like for the second half. Okay? And I believe that's what we just walked through, but there you go. And that may conclude the lecture. Let me double check my notes. I might go through some more stuff, or this might be the end of chapter 9, lecture B. Well, that is absolutely not it. Let's go through some more stuff. Some of this will be a review. And I'm going to set up the example problems for you, that you can work through the ones on your own. Again, with these worksheets, which are absolutely 100% me going through, these are absolutely designed so that if you follow the example steps, you get the right answer for the actual math that you're doing. So let's walk through that a little bit. So first of all, make sure I'm sharing the right screen. I'm pretty sure I am, but just want to make sure so you guys all get a great recording. Yep, absolutely the right screen. Okay, some definitions. The estimated standard error, SM, is an estimate of the standard deviation of a sampling distribution of sample means selected from a population with an unknown variance. It is an estimate of the standard error or standard distance that sample means deviate from the value of the population mean stated in the null hypothesis. The t-statistics, known as t-observed or t-obtained, is an inferential statistic that is used to determine the number of standard deviations in a t-distribution that a sample mean deviates from the mean value or mean difference stated in the null hypothesis. The t-distribution, or student's t, is a normal light distribution with great variability in the tails than with greater variability rather in the tails than a normal distribution, because the sample variance is substituted for the population variance to estimate the standard error in the distribution. The degrees of freedom, or DF, for a t-distribution are equal to the degrees of freedom for sample variance for a given sample n-1. Each t-distribution is associated with specified degrees of freedom. As sample size increases, the degrees of freedom also increase. The degrees of freedom for a t-distribution are equal to the degrees of freedom in sample variance n-1. The t-table, which is your unit normal table, lists critical values for 6 levels of significance for 1 and 2-tailed tests. 3 assumptions for a 1-sample test are normality, random sampling, and independence. Some definitions. The 1-sample t-test is a sample statistical procedure used to compare a mean value measured in a sample to a known value in a population. It is specifically used to test hypotheses concerning the mean in a single population with an unknown variance. Example 1, social functioning is the ability for an individual to interact or adapt in a normal or usual way in social environments. This area of research is of interest to the behavioral researcher, particularly in medical or clinical settings and those who study human development. As an example for the use of a 1-sample t-test, And clearly there's a spelling error there. We'll fix that right now. Albert et al., 2007, asked if relatives of patients with obsessive compulsive disorder, or OCD, are as healthy as those in the general healthy population. In their study, they recorded the social functioning of relatives of patients with OCD using a 36-item short-form health survey, SF36, with scores ranging from 0, worst possible health, to 100, best possible health. They cited that the mean social functioning score in the general healthy population of interest was 77.43. Using a sample data set that approximates their findings, we will test whether the mean score in the sample data given below significantly differs from that in the general population at a 0.05 level of significance. So here are our social functioning scores, okay? Just all right there. First step, we want to state that hypothesis. The population mean is 77.43, and we are testing whether or not equal or not equal the population means differs from the sample mean. So the null hypothesis is that the mean is equal to 77.43 for relatives who care for patients with OCD. The mean social functioning is 77.43, the same as that in the general healthy population. Again, null hypothesis, no relationship. For the alternative hypothesis, for relatives who care for patients with OCD, the mean social functioning score is not equal to 77.43. Step 2, set the criteria for a decision. The level of significance for this test is 0.05. We are computing a two-tailed test with n-1 degrees of freedom. With n equals 18 degrees of freedom in this test, or 18 minus 1 is equal to 17. To locate the critical values, we find 17 listed in the rows of table C.2 in Appendix C, which is that posted unit normal table in the classroom in Brightspace. And go to the column for the 0.05 proportion of the two tails combined. The critical values are plus or minus 2.110. So what we're talking about, if we do the whiteboard here, is we're literally talking about where are our cutoff regions. So conceptually, what we're talking about is here are our cutoff regions, okay? This is for the two-tailed test, plus or minus 2.110, 2.110 on both sides. Of course, this will be your negative, this will be your positive. And then, like I mentioned before, if it's at the cutoff region, like right on the spot, or if it's to the left or the right, depending on if we're talking about this one over here or this one over here, here's where we retain the null hypothesis, retain the null hypothesis. If you're here in the curve, retain. And then, of course, here's where we're going to reject. And it's the same thing on both sides, okay? So you reject here, and you reject over here too, okay? Just draw a link in here, okay? Like both of these are reject, that's retain. That feels pretty clear. Therefore, let's go back to our document here. Desktop 2. And when I refer to the shaded regions, what I'm talking about are the ones that are in the rejection region, okay? So we'll compare the value of the t-statistic to these critical values. If the value of the statistic is beyond a critical value, either greater than or less than plus or minus 2.110, there is less than a 5% chance we will obtain that outcome if the null hypothesis were correct. So we will reject it. Otherwise, we retain it. Again, that bell curve before the cutoff region, retain. At the cutoff region and beyond, reject. Compute the test statistic. In this table, we can compute the sample mean and the standard deviation for the given data given in the table above. As introduced in the past, the sample mean is the sum of all scores summed, and mean is 62. And to compute the sample standard deviation, first subtract and square the difference of each score from the sample mean divided by n-1, and then take the square root. The standard deviation would equal 20.94. We then compare the sample mean to the population mean stated in the null hypothesis. The mean is 77.43. To find the t-statistic, we first compute this estimated standard error. To compute the estimated standard error, which is the denominator of the statistic, we divide the sample standard deviation by the square root sample size, or n. In this example, standard deviation is 20.94 and n is equal to 18. Therefore, the standard error is equal to the standard deviation divided by the square root of n, 20.94, which is the standard deviation divided by the square root of 18, which is equal to 4.94. So the standard error is 4.94. You find this t-statistic by substituting the values for the sample mean, m equals 62, and the population mean stated in the null hypothesis, 77.43, and the estimated standard error we just calculated. Therefore, the standard error, estimated standard error is 4.94. The t obtained value is mean minus the sample mean minus the old mean, okay, divided by the standard error. 62 minus 77.43 divided by 4.94 is negative 3.126. Now we make a decision to decide to reject or retain the null hypothesis. We compare the obtained value, t is equal to negative 3.126 to critical values. Negative 3.126 falls beyond the critical value in the lower tail. It falls in the rejection region. The decision at this point is to reject the null hypothesis. Now, using the same set of data we just looked at, from the same form, using the following set of data. So the following, this is your data right here, okay, as I scroll down. What we want to look at is a group of 20 people. So your n is going to be 20 this time, but your degrees of freedom, of course, will be 19, n minus 1. So if this group of people with OCD are as healthy as those in the general healthy population, and we're going to use the same population, healthy population of interest, 77.43. So literally follow the steps I just walked you through, and you'll totally get that problem right. It's very likely you will. FYI, the t-table lists critical values for t-distributions with various degrees of freedom. The t-statistic for a one-sample t-test is the difference between the sample mean and the population mean, is stated by the null hypothesis divided by the estimated standard error. The sample standard deviation is used to estimate the population standard deviation in the estimated Cohen's d formula. Definitions: an estimated Cohen's d is a measure of effect size in terms of the number of standard deviations that mean scores shift above or below the population mean stated by the null hypothesis. The larger the value of Cohen's d, the larger the effect in the population. The proportion of variance is a measure of effect size in terms of the proportion or percent of variability in a dependent variable that can be explained or accounted for a treatment. In hypothesis testing, a treatment is any unique characteristic or of a sample or any unique way that a researcher treats a sample. The formula for Cohen's d is the following: d is equal to the sample mean minus the regular mean divided by standard deviation. So in the above example, d is 62 minus 72.43 divided by 20.94, which is equal to 0.074 to solve for d. So now do the same thing based on the example I just showed you from example 1 for the second set of data you just worked through. Some additional notes. The proportion of variance is variability explained divided by total variability. You also have what's called ETA squared. ETA squared is a measure of a proportion of variance that can be expressed in a single formula based on the results of a test. So how we do that is n squared is equal to t squared divided by t squared plus degrees of freedom. Now, make sure you're following PEMDAS. What I'm talking about is the order of operations. You want to go in the right order, which is your multiplication, division, addition, subtraction. So if you're unsure about that, you may want to look up PEMDAS or just order of operations. Just Google order of operations, and you'll get something walking you through that. That will be correct if you're unsure about like which ways to solve this. Now in this formula, you can check it. If you don't get the right answer, your order of operations is out of whack and you want to redo it so you get the right one. Okay, so formula in terms of order of operations, using lots of brackets. If you're using, say, like a scientific calculator, that'll usually help you sort of automatically do it. So in this formula, t is the value of the t statistic and df is the degrees of freedom. In this example, t obtained value is negative 3.126, which we previously calculated, and degrees of freedom is equal to 17. To find variance, we square the standard deviation. Thus, in the ETA squared formula, we square the value of t to find the proportion of variance. The proportion of variance for the data in the first example walkthrough is negative 3.126 squared plus 17, which is equal to 0.360. So in this example, we conclude that 36% of the variability in social functioning, the dependent variable, can be explained by the fact that participants were relatives who care for patients with OCD, the treatment. So like you probably want to like bracket this when you do it. Like then you're probably going to do it right. Like I said, this should be what you're going to get. If that doesn't make sense, then you want to go back and do that again. And the reason we got 36 is we moved that decimal over 2 places. So now calculate the same thing in the previous one. Our next one is our W squared, okay? So omega squared, or W squared, is also the variability explained by a treatment divided by the total variability observed. The change in the formula proportion of variance is 1 subtracted from t squared, the numerator. So W squared, or omega, is equal to T2 minus 1 divided by T2 divided by degrees of freedom, T2 plus degrees of freedom. So subtracting 1 in the numerator reduces the estimate of the effect size. Hence, the omega squared will always give a smaller, more conservative estimate of effect size, making it less biased than the ETA squared. Using the omega squared formula, the proportion of variance for the data in the first example, n equals 18, is W squared is equal to negative 3.126 squared minus 1. Negative 3.26 squared plus 17 is equal to 0.33. So we conclude that 33% of the variability in social functioning, the dependent variable, can be explained by the fact that participants were relatives who care for patients with the OCD, the treatment. If you find that the value of the ETA squared is also a large effect size because of what it is. And you can go ahead and explain, you can conclude for W2 for the previous one. Now, the SPSS, let's do that as a group, okay? So let me walk you guys through that. All right, guys, let's walk through the SPSS part of that assignment because you may not have that right in front of you, but no worries, this lecture will walk you through it. So first of all, we know that SPSS can be used to compute the one sample t-test. To illustrate how to compute the SPSS and how output tables in the SPSS match the data computed by hand, let's compute this test using the same data given for the OCD of 18 relatives with people who care for their patients with OCD. So we want to start by clicking on our variable view tab, okay? So you're going to want to click on this right here. I'm darn sure I'm sharing this correctly. Just want to make sure you guys can absolutely see that. Yeah, you guys can absolutely see that. Okay. So we're going to click on our variable view tab, and then we're going to label stuff. So first, we're going to enter. First, we're going to enter health in the column here. Okay. So going to go right here. We're going to name this. Not we, we're gonna name this health. Okay, and then we're gonna make the decimals 0, okay, like that. Then we're gonna click on the data view, which is gonna be right over here. Okay, so now we're gonna enter the 18 values that were in the worksheet, if you're wondering where those are. But I'll enter those for you, and that's going to look something like this. We had 20, and then we had 60, and then we had, I believe it was 48, and then we had 92, and then we had 50, and then we had 82, and then we had 48, then we had 90, and then we had 30, and then we had 68, and then we had 43, and then we had 54, and then we had 60, and then we had 62, and then we had 94, and then we had 67, and then we had 85. Is that all of them? I think I missed one. Let me see. We had, yeah, 20, 60, 48, 92, 50, 82, 48, 90, 30, 68, 43, 54, 60, 62, 94, 67, 63, and then 85. Okay, that's where I went wrong. Make sure you put all those in there. Okay, so then we're going to go to the menu bar. We're going to click on Analyze right here. And then we're going to click on Compare Means. And then we are going to go to the one sample t-test like that right there. And then you're going to get a nice pop-up. And then what you're going to do is, next thing is we're going to put our test variable over here like that. That's the test value. And we want to make sure that our test value is 77.43, that mean that we previously looked at. And then we're going to say, okay. And then what's going to happen is we're going to get our t-test right here. Let me move that over so you guys can see that. And then all you have to do for this part is, so you're going to see that, take a look at that, make sure that you're getting those answers, which is exactly what we were looking at just now, okay? And then I just want you to save it. So you go File, Save. You want to say Read and Write. And then you're going to give it a name. So you say something like Chapter 9 SPSS. You can say 996 because that's what we did, and then save. And then just take it and grab this file right here, go File, Save. And this is so that you have an SPV, which was your output file. And then you're going to have your SAV right here. And you can say chapter, something like Chapter 9, 9 SPSS data would be just fine, just so I know what it is. And then just upload those files in a Brightspace. I'll be able to read them. If you want to be fancy, you can export it like I mentioned in the past. You can do File, you can tell it to export it. You can make it into like Excel or a PDF file. I think it'd just be easier if you all just submit it as an SPSS file, which is the .spv is your extension for your output file, which is literally right here. And your SAV, which is literally this one right here, your data files. So just upload both of those files. So moving on, we'll go back to our Word doc. So that's the SPSS part. So that's what I wanted you guys to do. So now that's recorded. So that'll walk you through that. And then let's see, I believe this is right here. Yeah, there we go. Let's go back to that and just a few more definitions. That'll conclude this lecture here. Hopefully that's making it clear. Like I said, as I record these, if we need to take a little extra time here and there so you have the chance to digest this, I'm totally open to doing that. So some more definitions. An independent sample is a type of sample in which different participants are independently observed on time in each group. The two independent sample t-test is a statistical procedure used to compare the mean difference between two independent groups. This test is specifically used to test hypotheses concerning the difference between two population means, where the variance in one or both populations is unknown. Notes: for a two independent sample t-test, we make four assumptions. One, normality. Okay, that's our bell curve. We assume that data in each population, being the sample, are normally distributed. This assumption is particularly important for small samples because the standard error is smaller and this assumption becomes less critical as a result. Random sampling. We assume that the data we measure were obtained from samples that were selected using a random sampling procedure. It is generally considered inappropriate to conduct hypothesis tests with non-random samples. Independence, we assume that each measured outcome or observation is independent, that meaning that one outcome does not influence another. Specifically, outcomes are independent when the probability of one outcome has no effect on the probability of another outcome. Using a random sampling usually satisfies the assumption. Equal variances, we assume that the variances in each population are equal to each other. This assumption is usually satisfied when the larger sample variance is not greater than 2 times the smaller. Therefore, larger s squared divided by smaller s squared will be less than 2. 4 assumptions for a 2 independent sample t-test are normality, random sampling, independence, and equal variances. We can add the degrees of freedom for each sample to find the degrees of freedom for a 2 independent sample t-test. The 2 independent sample t-test measures the number of standard deviations in a t-distribution that a mean difference between groups deviates from the mean difference stated in the null hypothesis. The pooled sample standard deviation is used as an unbiased estimate for the standard deviation of the difference between 2 population means in the formula estimated for Cohen's d. Proportion of variance is calculated using the same formula for 1 sample and 2 independent same t-tests. Omega squared can only be computed for a test when t is greater than 1. Some additional definitions. The estimated standard error for the difference is an estimate of the standard deviation of the sampling distribution of mean differences between 2 sample means. It is an estimate of the standard error or standard distance that mean differences can be expected to deviate from the mean difference stated in the null hypothesis. The pooled sample variance is a mean sample variance of 2 samples. When the sample size is unequal, the variance in each group or sample is weighted by its respective degrees of freedom. The pooled sample standard deviation is the combined sample standard deviation of 2 groups or samples. It is computed by taking the square root of the pooled sample variance. This measure estimates the standard deviation for the difference between 2 population means. Now we're going to do the exercise in 9.9. Don't worry, you don't have that. That's something that I'm pulling from additional resource. I'm going to walk you guys through it. So let's go back to our SPSS. Should be right here. Actually, we'll stop the share temporarily just to make sure we have our SPSS doing what we want it to do. And in fact, I'll just pull. All right, back to SPSS. This is our last step today, and we'll share this. So first of all, we're going to want to have a brand new SPSS file. So if you're doing this in one sitting, click on File right here, and just new, and you just want a new data file, okay, just like that. And then we move this over here so you guys can actually see it. Here is our brand new data file. So just move the way I'd like it to. All right, a little bit of technical difficulties, and here we go. All right, so it's a brand new data file, all right, like that. And it will probably be wise at this point to close your SPV file, just because we only want to have separate documents for submitting here. Okay, so brand new file. All right, so SPSS can be used to compute 2 independent sample t-tests. To illustrate how we can do this, let's use some data with 2 groups that are eating slowly or groups that are eating fast. So we're going to click on the variable view tab right here, okay? And then we're going to type in groups in the name column. And in the second row, we're going to put intake. So we're going to put groups like this. Groups. And then we're going to say intake like that. And we're going to make our decimal 0 also, okay? So in the row label groups, we're going to click on the small gray box with 3 dots in the values column right here. And then in the dialog box 1, we're going to enter 1 here, and we're going to type slowly. This is the group that was eating food slowly. and then we're going to click on add. Then we're going to say 2, and we're going to enter fast. This is a group that ate their food fast, and we're trying to measure calories for the 2 different eating groups, like that. Pretty easy. So now we're going to go back to our data. So we're going to say, okay. And we're going to go back to our data. And what we're going to do is we're going to enter, in the groups column, we're going to enter 1 in the first 6 cells and then 2 in the next 6 cells. And then in the intake column, we're going to enter the calories that they ate for each group to correspond. So it's going to look something like this. We're going to have group 1, first 6 right here, and group 2, second 6, just like that. Then we're going to do the intake. So the first group, it was 700 calories, 450. This is our slow group. This is 850. Then we have 600, and then we have 450, and then we have 550, like that. Now, for the other group that ate faster, we had 450 calories. Then we had 800. Then we had 750 and 750. And then we had, 700, 750 and 700, my bad. And then we had 550. And then we had 650, like that. So now we're going to go to the menu bar. We're going to click on Analyze. And then we're going to go Compare Means again. And then we're going to do the independent sample t-test, right? Like that. And then we're going to use the arrows and select intake and move it into the test variables. And then we're going to put the grouping variable of groups into that box like that. And to define groups, we can enter group 1, enter 1 group. Well, yeah, I'm going to say group 1 is group 1. We already defined these. And group 2 is group 2. Because we already said they were fast and slow. No need to even say anything with a cut point. So we'll say okay. We'll go like that. Say okay. And then slowly, is that right? Yep. And then we get this output file like this. Now SPSS has done it for us. So we have a 95% confidence interval. We have our standard error of the difference. We have our T and our degrees of freedom. That's what we want to look at the most, the mean difference, which is right here. So we also have this, our T, our obtained value. So this shows our output. The thing we want to focus on the most is the top table displays the sample size, the mean, standard deviation, the standard error for both groups. The bottom table displays a summary for the t-test. The effect size is not given, although you can use the data in the output tables to compute the effect size. Also, if you notice, the bottom table gives the numerator and the denominator for the t-test, which it does, which this is our numerator right here, and our denominator is right here. Numerator, denominator, mean difference over the standard error difference, okay? That is our t obtained value. So t obtained value is this minus this. So if we were to whiteboard this, what you'd want to think about and remember would be this right here. We show the whiteboard. So you have your t obtained value, OBT, which is going to be equal to the mean difference, which SPS just told us. This is our mean difference divided by our standard error difference, okay? Mean difference, and this is our standard error, or SM. We can say, we can write out standard error, but actually let's just say standard error, just keep it easy. Standard error, standard error difference. And that's where our numerator and our denominator are different. I'm trying to type with the mouse here, so bear with me. So that's our t obtained value. So going back here, so this was our -50, okay? -50 right here. And then this was, of course, our 82.66 for our numerator and our denominator. And that can literally be found right here, okay? Bam, right there, all right? So the next thing we want to talk about is the remainder of our worksheet here, which I believe I can just pull right back up. Yeah, so there we go. So just to summarize a couple things here. So we just did all of this right here. And that takes us to the end, actually. So that concludes this lecture. And I will go ahead and get this posted and recorded. And I'll be posting a lecture on chapter 10 shortly. And as we approach the 9th, if we need a few more days, I will totally add that. But these lectures will be coming very soon and will be posted in Brightspace. Please continue to call and ask questions if you need help with anything at all. Rachel and Cam, I'm totally here for you. And I think you'll probably do all right in the class. Just keep talking to me. So here's your lecture, chapter 9, lecture B conclusion. Hope you learned something, and I'll see you in the next video. Take care, Rachel and Cam.